In this presentation, we are going to discuss one problem based on translational mechanical systems. So, let's get started. Find the transfer function gs equal to x2s over f of s for the translational mechanical network shown below. One translational mechanical system is given to us and we need to find out the transfer function gs equal to x2s over f of s. If we observe this translational mechanical system carefully, we can see that there are two masses m1 and m2, each of mass 1 kg, and they are connected with a spring and a damper. The spring is having the spring constant 1 Newton per meter and the damper is having the coefficient of viscous friction equal to 1 Newton second per meter. A force F of t is applied on this mass m1 to the right hand side, and due to this there is a displacement on mass m1 x1t to the right hand side. Moreover, from the previous lectures we already know that if spring and a damper are attached between two masses, then the forces on these two masses will not be the same. And hence, if the force Ft is applied on mass m1, then the force being applied on mass m2 will be different. And hence the displacement is different, which is x2t to the right hand side. We can note one more thing here. This fixed surface is frictionless. It means that we do not have to consider the friction between the masses and the surface. So more or less we can see one thing here, that due to the application of force F of t to the right hand side, this complete system will move towards the right hand side. And we need to find out the transfer function gs equal to x2s over f of s, where x2s is the Laplace transform of x2t, which is the displacement of mass m2, and f of s is the Laplace transform of ft, which is the force applied on mass m1. So I hope you understood this mechanical system. Let us now move on to the solution. The very first point that we need to understand regarding this mechanical system is that this system is an example of 2 degrees of freedom. That is, we are having two different masses m1 and m2 in this system, and each mass can be moved in the horizontal direction while the other is held still. That is, if we hold this mass m2, m1 can be moved in the horizontal direction, and similarly, if we hold this mass m1, then m2 can also be moved in the horizontal direction. In this case, since the force Ft is applied in the right hand direction, both the masses will move to the right hand side. We will discuss this in detail in a while. Moving on, if you remember that example that we discussed in the previous lecture, that mechanical system was having only one mass, and that's why we had to create the free body diagram of that one mass. But in this case, we are having two masses m1 and m2. And that's why in order to create the equations of motion, we have to create two different free body diagrams. One for the mass m1 and the other one is for the mass m2. So we can say that two equations of motion are required to describe the system. And that's why we need to create two different free body diagrams. One for the mass m1 and one for the mass m2. Moreover, superposition theorem is used to form the equations. So when we'll create the free body diagram, we'll be using the superposition theorem in order to create the equation of motion. I'll explain you that how we will do it. So in this way, we now understand that this mechanical system is an example of 2 degrees of freedom, and hence two equations of motion are required to describe the system, and we will get those two equations of motion by creating two different free body diagrams, one for the mass m1 and one for the mass m2. And while creating the free body diagram, we'll use this superposition theorem. Let us now move on to step number 1, in which we will draw the free body diagram for mass m1. So moving on to create the free body diagram, that is the FBD of mass m1. So let us consider the given mechanical system one more time. And we know that this system is an example of 2 degrees of freedom. That is, if we keep the mass m2 still, then we can move the mass m1 in either direction. And similarly, if we keep the mass m1 still, that is, if we hold the mass m1 and do not let it move, then also we can move the mass m2 in either direction. But in this case, we are applying the force F of t to the right hand side, and that's why all the motions will occur to the right hand side. So in order to draw the free body diagram of mass m1, we will follow 3 different steps. In step number 1, we will hold the mass m2 as still, and we will move the mass m1 to the right hand side. and we will analyze the number of force experienced by the mass m1 in this situation, and we will draw a separate FBD for that. Now in step number 2, we will hold the mass m1 as still and we will move the mass m2 to the right hand side. And in this situation too, we will analyze the number of force acting on mass m1. And in step number 3, we will take the superposition of these two cases in order to draw the complete free body diagram of mass m1. You will understand all these things when we will draw the free body diagram step by step. So let us start with step number 1, in which we will hold the mass m2 and move the mass m1 to the right hand side. So let us consider the mass m1 separately, and in this case we are holding the mass m2 and moving the mass m1 to the right. So let's analyze the number of forces experienced by m1 in this case. Let us consider the mass m1 separately. Now tell me, what will happen if we hold the mass m2 and move the mass m1 to the right? Yes, this spring and this damper will compress because this mass m2 is not moving and we are trying to move this mass m1 to the right. So this will lead to the compression of the spring and this damper. And at the same time, this spring will try to regain its original position by applying an opposing force, and this damper will oppose the relative motion by applying an opposing force. So let's now analyze the number of forces experienced by m1. The very first force is the applied force Ft, which is applied to the right hand direction. This is the applied force which is applied to the right hand direction. Then the first opposing force will be the force of the spring because it will try to regain its original position. And what will be the direction of this force? It will be towards the left hand side because we are trying to analyze the forces experienced by m1. So the second force will be the opposing force of spring, which is equal to 1 multiplied with x1t. In this case, the spring constant of spring is equal to 1 Newton per meter and the displacement experienced by the spring is x1t. The second opposing force is the opposing force due to this damper, so it will be equal to 1 multiplied with dx1t over dt, where the frictional constant is equal to 1 and dx1t over dt is the velocity of mass m1 to the right. Since the displacement is x1t, the velocity will be dx1t over dt, right? Now, is there any other force experienced by mass m1 in this situation? Yes, the force due to acceleration. If we are trying to move this mass m1 to the right, then due to this own mass, it will try to oppose the change in its position. And that force is directly proportional to acceleration that we know. So the third opposing force will be 1 multiplied with d squared x1t over dt squared, where the mass m1 is equal to 1 kg and the acceleration is d square x1t over dt squared. So these are the total number of forces experienced by the mass m1 when we are holding m2 and moving m1 to the right. I hope you got this. Let us call this diagram as figure A. And now we will move on to the step number 2, in which we will be holding the mass m1 and moving m2 to the right. We will be holding the mass m1 and we will try to move the mass m2 to the right. And in this case also, we will analyze the forces acting on mass m1. So let us consider the mass m1 separately one more time. And in this case, we are holding the mass m1 and we are moving the mass m2 to the right. Now what will happen if the mass m2 starts moving to the right? Yes, we can see that this spring and this damper are attached to this mass m2, and if we try to move this mass m2 to the right, then this will elongate the spring and the damper. And what will be the effect of this elongation on this mass m1? Yes, the spring and this damper will try to pull this mass m1 to the right hand side. But since we are holding this mass m1 as still, it will not move. So the first force that will act on this mass m1 in this situation will be the force due to this spring. So it will be equal to 1 multiplied with x2t, where the spring constant is equal to 1 and x2t is the displacement of mass m2. Now in this case, we are moving the mass m2 and the displacement of mass m2 is x2t. So the force that will be generated inside the spring will be proportional to the displacement x2t. And with this force, it will try to pull the mass m1. I hope you got this. In the same way, this damper will also try to pull this mass m1 to the right hand side. And we can indicate this force in this free body diagram as 1 multiplied with dx2t over dt. where the frictional constant is equal to 1 and dx2t over dt is the velocity with which the mass m2 is moving towards the right hand side. I hope you got this. Let me repeat the step number 2 one more time. In this situation, we are analyzing the number of forces acting on mass m1 when we are holding the mass m1 as still and moving the mass m2 to the right hand side. To understand this situation in a better manner, let us consider this complete system as a train in which the mass m2 is the engine which is moving to the right hand side and the mass m1 is the passenger compartment. And the engine and the passenger compartment are connected with these two connections. Now what happens when the engine moves forward to the right hand side? Yes, these two connections will try to pull this passenger compartment to the right hand side, and they will do it by applying a force to the right hand side. And that is what we have indicated in the free body diagram. The first force is the force due to spring, which is 1 multiplied with x2t, and the second force is the force due to damper, which is 1 multiplied with dx2t over dt. And the displacement is x2t because only the mass m2 is moving to the right hand side and it has the displacement x2t, and the mass m1 is kept still. So the net displacement in spring and this damper will be x2t. I hope you got this now. So in this way, we are done with the step number 2. Let us name this diagram as figure B, and we will now move on to figure C, in which we will consider the superposition of above two cases. So figure A represents the free body diagram of mass m1 when mass m2 is kept still and mass m1 was moving to the right. The figure B represents the free body diagram of mass m1 when mass m1 was kept still and mass m2 was moving to the right. Now if we take the superposition of these two cases, we will have the complete free body diagram of mass m1. So in order to take the superposition, let us consider the mass m1 one more time. And in this free body diagram, we will consider the forces of both these cases. So let us consider this case first. In this case, the first force was f of t. So the first force in this mass m1 is f of t. Then we have this opposing force of spring, which is 1 multiplied with x1t. Then after that, we are having this force of damper, which is 1 multiplied with dx1t over dt. Then after that, we are having the force due to acceleration. So it is 1 multiplied with d squared x1t over dt squared. And in this way, we are done with figure A. We will now consider the figure B. In figure B, the first force is the force due to spring, which is 1 multiplied with x2t to the right hand side. And the second force is the force due to damper, which is 1 multiplied with dx2t over dt to the right hand side. So we are now done with the superposition of these two cases, and we can say this is the complete free body diagram of mass m1. And we can now use this free body diagram in order to create the equation of motion of mass m1. So we will now move on to the calculation of equation of motion of mass m1 by using this free body diagram. Moving on to the equation of motion of mass m1. So let us consider the free body diagram that we created in the previous section. And we will now use this free body diagram in order to calculate the equation of motion. And we will follow the same sign convention that we discussed in the previous lecture. If the force is directed towards the right hand side, we will take that force as positive. And if the force is directed to the left hand side, we will take that force as negative. So starting from the first force, which is the applied force Ft, this force is applied to the right hand side, so we will consider this force as positive. Moving on, let us consider this force. It is directed towards the left hand side, so it will be taken as negative. So we will have minus 1 multiplied with d squared x1t over dt square. Now moving on to the next force, which is 1 multiplied with x1t. It is also directed towards the left hand side, so we will take this force as negative. So we have minus 1 multiplied with x1t. This force due to damper is also moving towards the left hand side, so we will consider this force as negative. So we have minus 1 multiplied with dx1t over dt. Moving on to the next force, if we consider this force, it is directed towards the right hand side, so it will be taken as positive. So we have plus 1 multiplied with x2t. And the last force is this force, and it is pointing towards the right hand side, so we will take this force as positive. So we have plus 1 multiplied with dx2t over dt. In this way, we are done with all the forces in this free body diagram. And now we know that according to the Newton's law of motion, the sum of all the number of forces acting on a body is equal to 0. So the algebraic sum of all these forces will be equal to 0. And this is the equation of motion of mass m1. It is f of t minus 1 multiplied with d squared x1t over dt squared minus 1 multiplied with x1t minus 1 multiplied with dx1t over dt plus 1 multiplied with x2t plus 1 multiplied with dx2t over dt equal to 0. Now, if we take the Laplace transform in this equation, we will have f of s minus s squared x1s minus x1s minus s multiplied with x1s plus x2s plus s multiplied with x2s equal to 0. We can apply the Laplace transform easily, and we all know that f of s is the Laplace transform of ft, s squared x1s is the Laplace transform of d square x1t over dt squared, x1s is the Laplace transform of xt, sx1s is the Laplace transform of dx1t over dt, x2s is the Laplace transform of x2t, and sx2s is the Laplace transform of dx2t over dt. Now, if we keep this term f of s in the left hand side and transpose all these terms to the right hand side, we will have f of s equal to s squared x1s plus sx1s plus x1s minus s multiplied with x2s minus x2s. If we take x1s common from these three terms and x2s common from these two terms, we will have f of s equal to x1s multiplied with s squared plus s plus 1 minus of x2s multiplied with s plus 1. And this is the force equation for mass m1. I hope you got this. In the same way, we have to create the force equation for mass m2. And for that sake, firstly we have to draw the free body diagram of mass m2. So in the next step, we will move on to draw the free body diagram of mass m2. In the previous section, we have discussed the free body diagram of mass m1 and we have calculated the equation of motion of mass m1. We will now move on to draw the free body diagram of mass m2. So let us consider the mechanical system which is given in the problem one more time. And now we will draw the free body diagram of mass m2. Again, we will follow the same three steps that we followed in the previous section in order to draw the free body diagram of mass m1. In the first step, we will analyze the number of forces acting on mass m2 by moving the mass m2 to the right hand side, keeping the mass m1 as still. In step number 2, we will analyze the number of forces acting on mass m2 by keeping the mass m2 as still and moving the mass m1 to the right hand side. And in step number 3, we will take the superposition of these two cases. But this time, we will perform all the three steps in a single diagram. So let us consider the mass m2 one more time. And in this case, let us consider the first situation. So what will happen if mass m2 is moving towards the right hand side and mass m1 is kept still? Yes, this spring and this damper will stretch to the right hand side. And what is the effect of this situation on mass m2? Yes, the spring will try to regain its original position by pulling this mass m2 to the left hand side. In the same way, this damper will try to oppose the relative motion by applying a force in the left hand side. So this mass m2 will experience a force on the left hand side due to the spring and one force in the left hand side due to this damper. So the first force that we will draw in the free body diagram is the opposing force due to the spring, which is 1 multiplied with x2t, which is directed towards the left hand side. The spring constant is equal to 1 and the displacement is x2t because mass m2 is moving towards the right hand side. In the same way, the second force is the opposing force of friction, which is 1 multiplied with dx2t over dt, where the frictional constant is equal to 1 and the velocity with which the mass m2 will move to the right hand side is dx2t over dt. Is there any other force in this situation? Yes, the force due to acceleration. If we try to move this mass m2 to the right hand side, then due to its own mass, m2 will resist the change in its position and it is directly proportional to the acceleration of this mass. So the third force, which is the opposing force, will be 1 multiplied with d squared x2t over dt squared, where the mass of m2 is equal to 1 kg and the acceleration is d square x2t over dt squared. I hope you got this. In this way, we are done with the first case in which the mass m2 was moving to the right hand side and the mass m1 was kept still. Now we will move on to the second step. So what will happen if mass m2 is kept still and mass m1 is moving to the right hand side? Yes, now this spring and this damper will compress because this mass m2 is not moving and this mass m1 is moving towards the right hand side. So this will compress this spring and this damper. And what is the effect of this situation in this mass m2? Yes, this spring will try to regain its original position, and due to this, it will push this mass m2 by applying a force on the right hand side. In the same way, this damper will also apply a force on the right hand side on this mass m2. So the force due to this spring on this mass m2 will be 1 multiplied with x1t, and it will act on the right hand side, where the spring constant is equal to 1 and the displacement in the spring is equal to x1t. Because mass m2 is now kept as still and mass m1 is moving, hence the net displacement in this spring is x1t. In the same way, the force due to this damper on this mass m2 will be 1 multiplied with dx1t over dt, and it will direct to the right hand side, where the frictional constant is 1 Newton second per meter and the velocity of mass m1 is dx1t over dt, since the displacement is x1t. So in this way, we are done with the first two steps, and the step number 3 is already done because we are taking all the forces in a single diagram, and hence this superposition is considered. So now we can say that this is the free body diagram of mass m2 for this mechanical system. And we are now in a position to calculate the equation of motion of mass m2. And keep in mind, we will follow the same convention. If the force is directed towards the right hand side, we will take that force as positive. And if the force is directed towards the left hand side, we will take that force as negative. So if we follow the convention, we will get the equation of motion as minus x2t minus dx2t over dt minus d squared x2t over dt squared plus x1t plus dx1t over dt equal to 0. We can see here, this force x2t is directed towards the left hand side, and hence we have taken this force as negative. In the same way, this force dx2t over dt is directed towards the left hand side, and hence we have taken this force as negative. Similarly, this force d square x2t over dt squared is directed towards the left hand side, and hence we have taken this force as negative. This force x1t is directed towards the right hand side, and that's why we have taken this force as positive. Similarly, this force dx1t over dt is directed towards the right hand side, and that's why we have taken this force as positive. And we already know that the sum of all the forces acting on a body is equal to 0, and that's why the algebraic sum of all these forces is equal to 0. And this is the equation of motion of mass m2. Now, if we transpose these three terms to the right hand side and take the Laplace transform, we will have x1s plus s multiplied with x1s equal to x2s plus s multiplied with x2s plus s squared multiplied with x2s, where x1s is the Laplace transform of x1t, sx1s is the Laplace transform of dx1t over dt, x2s is the Laplace transform of x2t, sx2s is the Laplace transform of dx2t over dt, and s squared x2s is the Laplace transform of d square x2t over dt squared. Now if we take x1s as common from these two terms and x2s as common from these three terms, we will have x1s multiplied with s plus 1 equal to x2s multiplied with s squared plus s plus 1. And this is the equation of motion for mass m2 in Laplace domain. In this way, we are done with the equation of motion of mass m1 and the equation of motion of mass m2. We can now completely define the system by using these two equations, and we are now in a position to calculate the overall transfer function gs. So we will now move on to calculate the transfer function gs. Moving on to the calculation of transfer function gs, which is equal to x2s over f of s. In this problem, we were given a mechanical system which was having two masses, m1 and m2, and that's why we had to create two equations of motion. So in the previous section, we created the equation of motion of mass m1 and the equation of motion of mass m2. Now we will use these equations in order to calculate the transfer function gs. So firstly, let us consider the equations of motion that we calculated in the previous section. The first equation is f of s equal to x1s multiplied with s squared plus s plus 1 minus x2s multiplied with s plus 1. And this is the equation of motion of mass m1. The second equation of motion is x1s multiplied with s plus 1 equal to x2s multiplied with s squared plus s plus 1. And this is the equation of motion of mass m2. Now we can use these equations of motion in order to calculate the transfer function x2s over f of s. And we can clearly see that in this equation, if we eliminate this term x1s, we can calculate the ratio x2s over f of s in order to calculate the transfer function gs. And for that sake, we will calculate x1s from this equation. So, if we transpose s plus 1 to the right hand side, we will have x1s equal to x2s multiplied with s squared plus s plus 1 over s plus 1. Now, if we put this value of x1s in this equation, we will have f of s equal to x2s multiplied with s squared plus s plus 1 whole squared over s plus 1 minus of x2s multiplied with s plus 1. We can see that the value of x1s was x2s multiplied with s squared plus s plus 1 over s plus 1, and we just put this value of x1s in this equation. I hope you got this. Now we have converted these two equations into one single equation by eliminating x1s, and we can now easily calculate the ratio x2s over f of s. So if we take x2s common from these two terms, we will have f of s equal to x2s multiplied with s squared plus s plus 1 whole squared over s plus 1 minus of s plus 1. If we take LCM in these two terms, we will have f of s equal to x2s multiplied with s squared plus s plus 1 whole squared minus of s plus 1 whole squared over s plus 1. Now we just need to simplify this equation in order to take the ratio x2s over f of s. So if we observe this term s squared plus s plus 1 whole squared, and if we consider s squared equal to a and s plus 1 equal to b, then it will look like a plus b whole squared. And we know that a plus b whole squared is equal to a squared plus b squared plus 2ab. So if we open this term with the identity of a plus b whole squared, this equation will look like this. F of s equal to x2s multiplied with a squared. In this case, a is equal to s squared. So a squared will be equal to s power 4 plus b squared. In this term, we assumed b equal to s plus 1. So b squared will be s plus 1 whole squared plus 2ab. So we have 2 multiplied with s squared s plus 1. I hope you got this. We just applied the identity of a plus b whole squared in this term by considering a equal to s squared and b equal to s plus 1. Now if we observe this equation, we can see that we are having a term of s plus 1 whole squared and a term of minus s plus 1 whole squared. So these two terms will cancel each other and we will have f of s equal to x2s multiplied with s power 4 plus 2s cube plus 2s squared over s plus 1. Now we can see that from these three terms we can take s squared as common. So if we take s squared as common from these three terms, we will have the ratio x2s over f of s equal to s plus 1 over s squared multiplied with s squared plus 2s plus 2. And this is the required transfer function gs equal to x2s over f of s, which is the answer to this problem. So in this way, we are done with this problem. This was a conceptual and lengthy problem. So I want you all to observe all the equations carefully and practice this problem one more time on your own. We will take some more problems based on translational mechanical systems in the upcoming lecture. As of now, we are done with this lecture. Thank you for watching this lecture. I'll end this one here. See you in the next lecture.